Okay, now we have about 15 minutes. That's good time for today and to move things forward. Now our Fourier transform toolbox is ready. So please carry it here and hereafter to this course, to the class in this course. It's very important. Now we are all set to switch between two very important domains, time and frequency. Let's remind ourselves that the complete definition of the electric field of a pulse is written this way in the notation that we evolved. E of t is the amplitude, the real amplitude, square root of I of t. I is real valued, remember, it is the absolute value square of some quantity. It is the envelope or the real amplitude is the square root of I of t multiplied by exponent of I omega naught t minus phi of t, and we took a half of this and plus the complex conjugate because E of t is real. Now Fourier transform this. Let's Fourier transform this quantity. E of t is complete, its amplitude and phase, the complete information is over here. Fourier transform E of t to E tilde of omega, right? What do we know? What do we know about E tilde of omega? What we know is the fact that this is also a complex function. Okay, so this complex function, okay, has two pieces. It is a sum of the Fourier transform of two pieces. The Fourier transform of this piece, a half square root of it, a real function, multiplied by e to the I omega naught t minus phi of t. All right, plus its complex conjugate, right? So now we need to first take the Fourier transform of this guy and then the complex conjugate. In doing so, we would then realize that this gives us two terms. The first term has a spectrum. The first term is a complex number or a complex function with the amplitude s of omega minus omega naught, where omega naught is this carrier frequency. Okay, and we have the exponential factor also over here, which now has again a phase function, now phi of omega, shifted by the same amount omega naught. Okay, now we had the complex conjugate of the same quantity. The complex conjugate yields a function which is identical in all respects. It is not a complex conjugate except for the fact that for the conjugate we simply have to replace omega by a minus omega both in the amplitude and the phase. Okay, so this is essentially a consequence of Fourier transforming this function, which is something plus its complex conjugate. All right. So the point here being this, that because we wrote the field like this, we get two pieces on the in the frequency domain also. Although electric field is real, and if I Fourier transform this, I would essentially get a spectrum which is going to look like, if this was a Gaussian, the spectrum would also look like a Gaussian. But owing to the maths and the way we have written it, we have a frequency domain description of the electric field which has both a positive and a negative frequency component. Since omegas are frequencies, they are all positive valued, positive numbers. The second term at the bottom is entirely on the negative axis. Okay, it is minus this one. This is minus omega plus omega naught, whereas this is omega minus omega naught. So this spectrum is spread across omega naught, the top piece. This is spread across omega naught, this is spread across minus omega naught. The frequency is spread, if you wish, but that's of course a mathematical, not artifact, a mathematical consequence. But important to note that these two terms are not necessarily complex conjugates of each other. Okay, that is the exponential terms. Here it is omega minus omega naught, whereas this is minus omega naught. It's not the I which is alone which is changing sign from minus I to plus I. Okay, so what are we going to do about this negative frequency aspect which came about as a consequence of the math? We are going to essentially focus on the fact that all we want to do is capture the information about the pulse, and our prejudice for the time domain comes in handy because think about all the action is happening in the time domain for a real valued electric field oscillating in the time domain, that real valued electric field propagating. Then essentially if I go back here, note now that S, this function, has the same form in both the positive frequency side and the negative frequency side. The amplitude has the same form, square root of the same function S. The phase part of the complex number again contains the same functional form phi, albeit centered at on either side of the zero of the frequency axis. But the information is pretty much the same. That is to say, if I keep track of this, I can essentially write everything else down completely if I so wish. So therefore, there is no new information contained on the negative frequency side, and that we state that explicitly because this bothers us, because in the real world there is no negative frequency, right? So now therefore we can only keep track, we only need to keep track of the positive frequency components side, as well as earlier we threw away the omega naught saying, okay, you are a central frequency or a number, I will bookkeep you, but then the rest is where again the action happens. So we can even center the pulse, we can even subsume that in a more compact notation. At its actual frequency, and we can really write this down in the frequency domain, a compact description where E tilde of omega. Now we can use this almost as a definition. E tilde of omega, the Fourier transform of E of t. Okay, E of t is real, it's real, essentially real value. Although writing it in the complex notation and such gave us something to worry about both on the positive and negative frequency side, we can stick to this complex frequency domain description of the pulse field as E tilde of omega to be this having an amplitude which now we write in the same way as we did in the time domain as the square root of S of omega, which is the spectrum of the pulse, which is a real valued number. Remember, the spectrum was and is always S of omega is the absolute value square of the complete Fourier transform, which is a complex valued function for the field. Take the square root of this S. This is the, again, real equivalent of the real amplitude in the frequency domain, if you wish, that is S of omega, and phi of omega. Phi of omega is the all important spectral phase, right? So therefore now, here and hereafter in this course, rather than say phase, we should care to say temporal or spectral. Okay, we have tried to use two different symbols for this, such as phi and phi. As though these two phi's are very different. Probably for us writing by hand, it's not even going to, we may even accidentally swap the two, I would certainly. So therefore, I would advise you to be more specific, to kind of write it like this. Sometimes in some literature, you actually see people or literature employing a subscript to designate a spectral versus a temporal phase, both of which are equally important. Albeit, if you do measure the spectrum S of omega, you will only be measuring the amplitude of this, something related to the amplitude of the electric field in its complex, in its frequency domain description. We wouldn't be measuring the spectral phase. But here is the point. We have methods to measure both these. We have methods to measure S of omega Okay, let me put this inside. Can be measured directly. That is to say, what do I mean by directly? It's like you have a device, or you can devise a device that can measure it straightforward. Phi of omega can also be measured somewhat directly. Although the measuring the phi of omega is going to take more effort. Or these two quantities, we do have a device that can these are both measurable. Now we should ask, or rather now we can make the point, what about phi of t? What about this? And what about I of t? How measurable are these? That is to say, can I figure out a device that will measure the temporal variation of intensity or the envelope of the pulse directly? In other words, you are asking for, if I were to talk about I of t, some kind of scope. I wouldn't call it an oscilloscope. An oscilloscope would have measured for you, an oscilloscope measures for you E of t at say frequencies even up to a gigahertz. Or if you want to add a 0 to 10 gigahertz, your budget also increases by the same factor or more. or maybe 100 times. So we have very expensive oscilloscope. But oscilloscopes, these scopes which can measure fields directly, okay, you have 1 gigahertz, maybe 5 or tens of gigahertz too. Let's say they exist somewhere at least. But then the fields that we are talking about have frequencies of the order of, our fields are 10 to the 14 hertz. Ouch! You see the problem? So do we have devices that can measure this? Are these directly measurable? Eventually, you can say sort of indirectly measurable. I don't want to use such a term. However, which of the two is more measurable? Which of the two domains do we think can actually are more amenable to measurement? Right now, we would immediately tend to say, oh, it's probably the frequency or the complex domain. I mean, but there is an example staring at us, or that we actually use to stare at. Eyes are sensitive to spectral information, color, but eyes are they sensitive to the oscillations in time of the electric field of the wave that we are perceiving? No, not at all. They are in some sense sensitive to the irradiance, but not so much the temporal variations of intensity if the temporal variation of the envelope is too fast. So maybe some level of measurement of this, but certainly to measure phi of t directly is almost next to impossible. It seems to be a very hard problem. In this course, we will see that for optical frequencies, attosecond pulses kind of enabled this. So you have a so-called petahertz oscilloscope demonstrated. But this is an oscilloscope within quotes. It's far from a scope that you can buy in the market as of today and just plug your, or couple your wave in through whatever. Here, if it's an optical field, not plugged through a metallic coax cable, but maybe an optical fiber, which of course these days carries our internet direct to home, I think. But then we are not yet there with the technology, but at least an in principle demonstration of this has been carried out, right? So, but it's as hard as that. Maybe a few labs in the world have been able to do it, and it's not something for a daily measurement. So the spectral domain quantities are far more measurable than the temporal domain quantities in these cases. Okay, so that's really the point of now describing the pulse and its frequency content this way. The same facts sort of visually, right? Now, Fourier transforming E of t, first of all, in the normal course, it gave us two pieces. A spectrum centered at some omega naught, like a carrier frequency. This was centered at omega naught, and all these were you can say that this is a spectrum which is a shifted version of this guy where omega naught seems to be a 0. This is the primary spectrum of this pulse, the way we had defined it earlier. This is essentially the spectrum of this guy, this function. The way we had written down the electric field earlier resulted in the spectrum being presented at a center omega naught which is not 0, and here centered at minus omega naught here being the positive valued number over here. So let me just emphasize its positivity by writing this as minus the absolute value of omega naught. Right? But then watch this figure carefully and we will close with this, an all important plot. On the horizontal axis you have omega. Here there are two vertical axes. This vertical axis on the left is intensity. All right, spectral intensity in some units. Sorry. Oh no, sorry. This is spectral intensity. So spectral intensity is S of omega. But here we used again another axis on the right. This axis on the right is that of the spectral phase, and that is sketched here in dotted lines, corresponding to each of these pieces of the spectrum. Now, what do you say about this chart? I say this is each of these, any of these pieces, either here the spectral intensity with the spectral phase, spectral intensity with spectral phase, or spectral intensity with spectral phase, but take any one of them. I say that this is a complete description of the pulse or the electromagnetic wave, the electric field. It's a complete description. It is equivalent to knowing or seeing E of t. It's equivalent, it's just that measuring the combo S of omega and phi of omega, these are infinitely more measurable than E of t directly at our petahertz frequencies. So that's the power of the frequency domain description. Nature gifts us a way to measure spectra, right from the eyes to many other ways. You can measure wavelengths, convert them to frequencies, you can count frequencies too. But here we are essentially, it turns out to be that this is a more direct wavelength measurement of quantities rather than a frequency counting, which is another technique. But the whole point is that these two quantities S of omega and phi of omega are both measurable, and more importantly, they carry the complete information that we need to know about this kingpin, the royal emperor E of t, about whom we want to know everything else, everything that can be known. Right, so the frequency domain description is equivalent to the time domain description, and we know everything if we know all about the frequency domain. Okay, that's really the take-home message of this lecture, and we know how to swap between the two thanks to Fourier transforms. Okay, so with that I will stop the lecture for today. Thank you.